Today we talk about minimal spanning trees and some similar problems like minimum obsolescence problem. Let's go. So minimal spanning tree. Let's have some undirected graph. We have some undirected graph. Let's say something like this. Something like that. So the spanning tree is a tree which contains all the nodes of your graph. So if your graph is connected, it always contains some spanning tree. For example, you can make something like, you can make a depth first search and take this depth first search tree as a spanning tree. So every tree which contains all the nodes of your graph is a spanning tree. For example, let's put something like this. So for example, if we take this edge, and let's say this edge, then go here, then take this edge plus this edge, and let's say something like this and this. So if you take these edges of your graph, you will have some spanning tree of your graph. That's simple. So what are we trying to find? We're trying to find a minimal spanning tree. What is minimum? Imagine each edge has some weight. For example, let's put some weights on all edges. Let's say you have 6, then 3, then 4, and 8. It's 8. And 5, and say 10 here, and 1 here, 3 here, and 5 here, and 6 here, and 2, and 7, and 10, and 6 again, and I don't know, 5 when. So if you have a tree like this, the weight of the tree is just the sum of all weights of all edges. For example, for this tree, the sum will be 5 plus 3. 8, 9, 12, 16, 21, 23, 29, right? So the weight of the tree is just sum of all weights. It is 29 for this tree. Now, what we try to do is we try to build a spanning tree with minimal total cost of all edges, total weight of all edges. You can call them costs or weights, it doesn't matter, we have only one value, so it doesn't matter how we call it. So that's the whole problem. You have a graph, each edge has some cost or some weight, and we want to find some connected structure with minimal total sum. And it's quite useful. For example, if you just want to connect all the nodes, you have some nodes of your graph and you want to somehow connect all of them. So the minimal connected structure of the graph is some spanning tree. Yeah? If you have a cycle, you can always remove one edge from the cycle and the total sum will be decreased. If all weights are non-negative. So the minimal structure which connects all the nodes of your graph is some spanning tree. And we want to find the spanning tree which have minimal total cost, minimal total weight, something like this. That's the whole problem. It's actually quite simple. Now, to solve this problem, there are many interesting algorithms. Most of them are based on the same lemma. So first, before we discuss all these algorithms, I will prove one simple lemma. It looks like this. Imagine you split the nodes of your graph into two groups. So you have all nodes of your graph, you just split them into two non-intersecting sets. So first set will be A and second set will be B. And now you look on all edges which connects A to B. So you look on all edges between these two sets. Now, let's find the minimal edge among all edges in this group. So we find the minimal edge in which connects A to B. It's actually called a cut. So when we will discuss flows, it will make much more sense. But right now it's not important. So if you know how the maximal flow works, it's kind of the same, but it's not that important. So we just split all the nodes into two groups and look on all edges which connects these two groups. Now, let's take the minimal edge among all these edges. So we'll find the edge UV such that it has minimal weight and U is in A and V is in B. Let's find this edge. This edge. So this is the minimal edge. Yeah, that's a nice shirt, yeah. It's one of the Kotlin Heroes round, yeah. I always participate in Kotlin Heroes rounds just because of the t-shirts, yeah. So, let's find this minimal edge. Now, the lemma is very simple. If you have this edge should belong to some minimal spanning tree. Sometimes there is not unique way to do. Sometimes there may be multiple ways to construct minimal spanning trees. So it belongs to some of minimal spanning trees. So if there are multiple spanning trees, then it belongs to one of them. For example, if all costs are equal, then any spanning tree is a minimal spanning tree. So. So it's sometimes it's not there's no unique way to construct a minimal spanning tree. But if this is the minimal edge among all these edges, then there is some minimal spanning tree which contains the edge UV. Yes, if all the costs are pairwise distinct, then there's a unique way to construct minimal spanning tree. We will prove it in a moment. We will prove it. Right now it's not that obvious, but it's actually true. Yeah. But if you have equal cost for some edges, then there may be different ways to construct a minimal spanning tree. In that case, there is some minimal spanning tree which contains the edge UV. Yeah. Well, let's prove this. No, let's prove it. So let's take some minimal spanning tree. Let's look on this main spanning tree. In this minimal spanning tree, nodes U and V must be connected. It's literally written on the board here. So UV is the minimal edge among all edges such that U belongs to A and V belongs to B. So we split all the nodes of graph into groups and take the minimal edge between these groups. Now, let's take this minimal spanning tree. In this minimal spanning tree, nodes U and V are connected somehow. So there is a path which belongs to the MST which connects U to V. So there is some path. This path is inside MST. Yeah. So there must be some path from U to V such that all edges on this path belong to MST. Now, U belongs to set A and V belong to set B. So on this path, at some point, we must switch from A to B. So in this path, there must be some edge. Let's say edge xy, such that x belongs to A and y belongs to B. So for this edge. Now, what can we do? We can take this minimal spanning tree, remove this edge xy, and add this new edge uv. We will get again a spanning tree. And the cost of this spanning tree will be not greater than the cost of this spanning tree, because we have the minimal edge, so the cost of the edge uv or uv is not greater than the cost of edge xy. So if we remove edge xy and add edge uv, we will have another spanning tree, and the cost of this tree will be not greater than the cost of that tree. So now we have the minimal spanning tree which contains the edge uv. That's all. That's the whole proof. Why does the spanning tree? No, let's prove this. Okay. Let's prove. Let's prove this is tree. It's actually quite simple. Okay, easiest way to prove this is just to prove that all the nodes are connected again. So we have the number of edges is the same. If we prove that all nodes are connected, then we prove that we have a tree, right? Now, how to prove all nodes are connected? Let's take any two nodes and look on the path within these two nodes. If this path contains this edge xy, then instead, so let's take any two nodes, A and B. Yeah. These two nodes was connected in this graph, so we had some path. Now, if this path contained xy, then we remove this xy and add this edge instead. So instead of this xy, let's add all this path containing node uv. And now we have path from A to B. So every pair of nodes is connected again. That's one of the way to prove this. Another way is just to look what happened if you add if you add edge to the tree, you will have some cycle, right? Now this cycle contains this edge xy. So now you have just a tree with one extra edge. So you have this tree and one extra edge. So you have this cycle and something here. So after you add this new edge uv, you will have situation like this. Now you remove one edge from this cycle, this edge, and now again you have a tree. That's just more visual way to prove this. Okay. Cool. Now that's the whole lemma. That's actually the only lemma we will need in this algorithm. Now let's build some algorithms from this lemma. We will learn 3 different algorithms. One of the most common algorithms is actually the Kruskal algorithm. How to spell it correctly? Let me check. Both K. So Kruskal algorithm is very simple. Let's take the graph. Well, let's move this graph. Just remove this by now. Let's take the graph. Let's find the minimal edge. So let's sort all the edges by the cost, by the weight, and take the minimal one. So for example, here we have this edge 1. Easy observation, this edge 1 should belong to some minimal spanning tree. Why this edge 1 should belong to some minimal spanning tree? Because we can look on any cut which contains this edge. For example, you can look on the cut from this node and everything else. Again, let's find this minimal edge. This minimal edge is a minimal edge in some cut. For example, we can take cut, we can say this edge is A and everything else is B. So this edge will be minimal edge in this cut. So minimal edge in this cut should belong to some minimal spanning tree. So let's just add this edge to the minimal spanning tree. So just take this edge, add it to minimal spanning tree. That's all. Now let's take the next edge. It will be this edge 2. This edge 2 also should be in some minimal spanning tree. Why? Let's take a cut from these two edges, or from these two nodes, and everything else. So this H2 is minimal edge in this cut. So it must belong to this spanning tree. So this, and so on. That's all. Now each time we just look on the minimal edge and try to add it to our spanning tree. It's too boring again. I don't know how to construct good graphs for these algorithms. So we add this 3, add this 3, add this 4, add this 5, add this 5. Now, at some point we will try to add this edge. So this edge shouldn't belong to a minimal spanning tree, because if we add this edge, we will have a cycle, and we don't want to have cycles in our spanning trees, right? So if we take the next edge in the sorted order and try to add this edge to our spanning tree, and we see that we will get a cycle if we add this edge to our spanning tree, then we just skip this edge and go to the next edge. What does it mean? It means actually that this edge is not minimal in any cards, because these two nodes are connected, so we have this path. So in any cut there will be this path, and all edges on this path are less than this edge. That's actually what this means. So if we have this edge, and if we try to add it, we'll have this cycle, then we just skip this edge and take the next edge. And so on. So we just skip this edge and find the next edge. This 6. If we add this 6, again, we will have a cycle. So we skip this 6, take this 6. This 6 will not form any cycle, so we add this edge and so on. That's the whole plan. So the plan is like this: sort edges. So E is just set of all edges, just for simplicity. Now we iterate over all edges. I'll use very strange language today. That's not usually how you write cycles and how you write loops in your programming language, but it's cool. So it is unique minimum. Yes. If this edge is unique minimum in the cut, it must belong to any minimal spanning tree. It's also correct. Yeah. We proved exactly like that. Yeah. Now, let's take some. Let's iterate over all edges in the sorted order. Let's try to, if this U and V are not connected in current LST, then we add this edge UV to MST. That's the whole plan. That's how it works. So we sort all the edges by the weight, and then iterate over all edges in this order. And if these nodes are not yet connected by this minimal spanning tree, we add this edge and connect them using this edge. That's the whole plan. Now, what is the fastest way to check if two nodes are connected? Yes, like you mentioned already in the chat, the easiest way, the data structure which answers these questions is the union find data structure from the previous semester. So we can use union find data structure or disjointed union, it's the other name of the same data structure. So we can use this union find data structure to check if two nodes are connected and to connect them. So let's modify it a little. So let's say if find of U is not equal to find of V, then we just make a union of U and V. Yeah. That's basically the whole Kruskal algorithm. It's pretty simple, it works pretty fast. So now let's talk about time complexity. What is the time complexity of this algorithm? What's the time complexity of union find? Let's start with this line and this line. So this line is executed m times, and this line is actually executed n times. Yes, we can use all the heuristics from the union find structure. It's just simple union find structure. You can use both the rank heuristics and path compression. Why not? So if you use both heuristics, the complexity of this operation will be alpha mn. But yeah, unfortunately, we also have this sort. And this sort is actually the most slow part of this algorithm. So the slowest part of this algorithm is actually sorting all the edges, by the way. This sorting costs m log m time. So the total time complexity, so this will be much less than this. So this is the slowest part. So total time complexity will be m log n. Yeah. Or m log n, it actually doesn't matter. So logarithm of m and n is actually the same thing. Yeah. Well, because the m is about n square, and logarithm of n square is about the same as logarithm n, just by constant factor. So it doesn't matter. It's a good question if it is possible to solve in linear time. We will talk about it in the end. Okay. The answer is actually we don't know. It's spoiler, but we'll talk about it in the end. Now, this is the first very simple algorithm which allows you to build the minimal spanning tree in this time. Now, the next algorithm is called the Prim algorithm. I need to erase something. Let's click on this. No. It's Prim, right? Just check. That's Prim. Okay. English is Rascals. Okay. English is difficult. Okay. Now, the algorithm. Let's use the same idea, but differently. Let's use differently. So again, let's look on this graph. Let's take the graph. Now, let's take any node of this graph and call this node a starting node. For example, let's take, I don't know, let's take this node and say this node is a starting node of the algorithm. Now, each time we'll do the following. We'll find the minimal edge in the cut from this node to everything else. So now we have only this node. So let's say this node belongs to set A. Everything else belongs to set B. Let's find the minimal edge between A and B. It will be one of these edges. Which one you like most? Let's take this node, edge for example. So we find the minimal edge between this A and everything else. This will be this edge. So we add this edge to the result and put this node in the set A. Now again, let's try to find the minimal edge between A and everything else. So we have this set A and everything else. Between this and everything else, this is the minimal edge. So we take this edge, add it to the result. Now put this node in set A. And so on. Each time we have some current set A and everything else. So we have some set A and everything else. We look on all edges here, find the minimal edge. Again, I just erased it. Okay. Minimal edge such that U belongs to A and V doesn't belong to A. And we add this edge to the spanning tree. So we add this edge to the spanning tree and now move this V to set A. Like this. But let me write a code. So first, set A contains only one node, S. So we start by putting one of the nodes of the graph into this set. And now each time Let me write it in Kotlin way again. I just like this. So we just repeat n minus 1 times the following operation. We take the minimal edge between A and everything else. So let's take, I will just write a pseudocode, very pseudocode. It will be the minimal edge such that U belongs to A and V does belong to A. And we just add this UV to MST and add this V to set A. It's very pseudocode. Okay. Clear enough? Again, it's quite easy to prove that it is correct algorithm. Again, just by using the same lemma we proved in the beginning of the lecture. Yeah. Just every time we just apply the same lemma. So we take some cut. In this cut we find the minimal edge, add this edge to the result, and so on. Then repeat this process until we have the tree. That's all. Now, what is the time complexity of this algorithm? No, again, time complexity. Actually, no, it's very pseudocode. Okay, so to find time complexity, we need to find the appropriate data structure. So we need to find the appropriate data structure, which allows us to find this minimum and make these modifications. So again, we need some data structure, which is good to find minimums. Okay? So we need to find these minimums, and we need to modify the set A. Yeah. There are actually two ways. So we will discuss two data structures we can use here. First, the first idea, let's just put all these edges into some priority queue. Yeah. Let's use some binary heap, for example. Let's just use binary heap to keep the track of all the edges between A and so on. Let me just do it here. So if we have a priority queue, and we'll just put all the edges we need into this priority queue. First we have this priority queue. It will contain all the edges from S to V. Yeah. All edges going from S to S. Now again, A is just S. Now we just again repeat n minus 1 times the following operation. We take the minimal element from the queue. Let's say remove min just for simplicity. And now we need to modify this set A. So when we add vertex V to set A, we actually need to modify the set which is currently in our queue. Because since we move this V to the set A, some edges should be put inside this queue, some edges should be removed from so. So let's iterate over all edges connected to this node V. So we have some edges like this. If this U is not in set A, if this vertex U is not an A, then we need to put this edge into priority queue. Because, again, before we have V not an A, U not an A. And now we have V in A, U not in A. So this edge should be put into the priority. And if not, then we actually need to remove this edge, because this edge is something like this. So if we have edge from V to something inside A, then now we need to remove this edge. Yeah, good enough. So, I think it actually should work just like this. Now let's look on time complexity. So what happens with time complexity? We use some priority queue operations here. We use it here and here. How many times did we call this operation? This operation is called n times, n minus 1 times. So we have n operations like this. And what about these operations? These operations are actually called for every edge of the tree. So every time we take every vertex will be moved to set A exactly once. So this V will be iterated over all nodes in graph, and each vertex V will be here in exactly once. So here we iterate over all edges of this vertex V. So we will iterate over all edges of the graph exactly once. So these operations will be called for each edge exactly once. So we have m operations like this. Of course, yeah, we will modify it a little. Yes, we will modify it shortly. Yeah, you're right. You're right. This is just the first version. Yes. I believe it's just more easy way to understand what's going on here. And we will improve it later. Yeah. So now, if you use any priority queue, basically, like binary heap, why not? Then you can achieve a complexity log n for all these operations. So both these operations will work in log n time. So total time complexity again will be m log n. Yep. Now let's try to improve it. How we'll improve this algorithm? No, let's see. We actually keep too many edges in our priority queue. Let's see again. So what's going on now? We have this set A and we have everything else. Yeah? And we just try to put all the edges between these two sets into our priority queue. That's too many edges actually. We don't need that many edges. For example, for each node which is not an A, we need actually only one edge. The minimal edge which connects it to set A. So if we have multiple edges for this node V, for all these edges, we only need to keep track of only one edge, which is minimal edge. If this edge is not a minimal among these edges, it will never be minimum among all edges. Yeah. So for each vertex V, which is not in set A, we need only to take care about one edge, which is the minimal edge. Let's do it. Okay. Version 2. Well, let me put. This graph is ruined, so. Okay. So the plan. For each node which is not in set A, we will remember the minimal edge which connects to. So let's say D of V is the minimal edge to set A. It's minimum of all weights UV such that U is in A. Now let's modify this order. So again, we do the same tree and so on. A is the set A's. For all V, we have D of V is cost of SV. That's all. That's just the initiation of the situation. Now we just repeat the same procedure. Yes, and we put them all in the queue. Yeah. Now, what we'll do, we will take the minimal D from all these elements here. So again, we want to find the minimal edge which connects set A and everything else. For each node, we remember one minimal edge. And now for all these nodes, we will take the minimal one. So we will take the minimum of all minimums. It will be the minimum of all possible edges. Once again, for each node here, we remember the minimal edge from all the edges which connects A to this node. And now we will take minimum of all these minimums. It will be the minimum of all edges. We kind of split all the elements into all these edges into groups. In each group we find the minimum, and now we take minimum of all these minimums. Right? So here we'll take this node V, it will be minimum in our queue. No, let's remove them. I'll just do it in one operation. I'll find it and remove it. Again, this priority queue, we have all the nodes sorted by this D, by this value D. If I remove the minimal element from priority queue, I will find the minimal value of D. So here is the minimal. Value D is by itself, it's a minimum of all ingoing edges. So for each node I have the minimum of all ingoing edges, and now I take minimum of all these minimums. It will be the minimum of all edges. Yeah? Yeah? No? I'll repeat again until you say everything is clear. Again, what's going on? Here, I want to implement this. I want to find minimal edge which connects something from something from A to something not from A. To do this, I will keep track of minimum for each node V. For each node V, I will take the minimum of all edges like this and put it here into DV. And now I take minimum of all possible D, and it will be the minimum of all edges. Okay, hope it's clear enough. Now, I find this node V. I need to move it to set A and modify the data structure. So how to modify the data structure? Again, if I move this node V to set A. Okay, this picture is ruined. Officially up. So when I move this V to set A, I need to look on all edges from this node V. So let's write all edges. For all edges VU. And no, right now here I just put this edge into the priority queue, but here is something different. Yeah, here I just need to update the value of D. So for these nodes, now I have one more edge connected to this node. So I just need to update this value. So I need to update DU as minimum of previous value and the cost of this edge. If the graph is not connected, you can always add some extra edges to make it connected. It doesn't matter. So I'll assume the graph is connected. If the graph is not connected, and you want to you build not a tree but a forest of trees for each connected, you can just split it into connected components and build a tree inside each connected component separately. It's easy. Now, that's all. So now we update the value of D. Now what we need to do is to update the priority queue, because in the priority queue we we sort all the elements in the priority queue by these values of D. So in the priority queue we take this minimum D, so all the elements in the priority queue are sorted by this value of D. So when we change the value of D, we can change the key in the priority queue, and we need to update the priority queue. So in the priority queue we need to update this element u. For example, if you have a binary heap, you need to sift this element up. So you change the key of the element, you need to sift it up to make the priority queue valid again, right? That's how I update elements. No, alternatively, you can just remove the element, update the value, and then put it back in the priority queue. That's one of the ways to do it. No announcement code forces. Okay, it's not always. I believe it's too late to make announcements. I believe everybody who wants to watch this lecture are here, so it's good enough. All the best viewers are here, I believe. Now, that's all. Now, let's calculate time complexity. Again, time complexity. Let's see. Yeah, let's look on all operations on the priority queue. We have this operation. This operation is called n times, like before. And this operation is called m times. Now again, if you just use a basic binary heap, then both operations will work in log n time. So if you use binary heap, let me erase this. So if you use binary heap, then both operations will work in log n time. So you will have n log n here, m log n here, so total time complexity will be m log n. But sometimes it's not the best data structure. For example, if m is big and n is small, then you kind of want to make this operation faster and this operation slower. And for example, you may use a very efficient data structure which is called an array. Yeah. So if you just use an array, array is actually efficient data structure if you want to find minimum, and you want that is useful data structure when you want to make updates faster. Yeah. So if you use array instead of binary heap, then here you will find minimum in linear time. So it will be n square for this operation. But the updates will be fast. You just update the element and do nothing. That's all. So these updates will work in constant time. So it will be n plus m. Which one is better, this or this? What time complexity is better, m log n or n square plus m? Yes. Yes, we'll use Fibonacci Heap in a moment. But let's just stop here for a second. So we have two possible implementations of this algorithm. One implementation works in m log n time, another works in n square plus m time. Which one is better? The answer is it actually depends on this ratio between n and m. For example, if your graph is very sparse, if you have very small number of edges, if m is about n, then here you have n log n, and here you have n square. And if the graph is very dense, so if m is about n square, then here you have n square log, and here we have just n square. So if you have a small number of edges, this algorithm is actually more efficient. If you have a large number of edges, then this algorithm is actually more efficient. It happens sometimes. Sometimes you have different time complexities. You can actually combine them, make some combined algorithm which looks on the value of m and n and combines them in some special way. So if you see that the number m is big, you use this algorithm. It's number small, you use this algorithm. And if you just fix some good construct, how it's called? No, you need to make some border between this and this. So if you just can distinguish when you can use this and when you can use this, you will have something optimal for both these cases. Yes, I do not forget. Another way to think about it is instead of using binary heaps or arrays, you can just use Fibonacci heaps. Yeah, that's theoretically it's more efficient. If you use Fibonacci heap, then here you need to remove minimum. You can remove minimum from Fibonacci heap in log n time. Yeah, so it will be n log. But this operation is actually decreasing the key in the Fibonacci heap because this d is always decreasing. Yeah, because it's minimum of previous value and this. So here in this line, you always decrease the key d, and you can decrease keys in Fibonacci heap in constant time. So this actually operation works in constant time, so with plus m. This complexity is better than both of this, yeah. So it's better than this, obviously, and better than this. So this kind of optimal of these three. Good, but it's theoretical in theory. In practice, Fibonacci heaps actually have a very bad constant factor. So the time complexity theoretical is quite good, but the actual time spent by your computer will be bad. So in most cases, you need to use one of these algorithms. Mostly this, but sometimes this is efficient. If your graph is very dense, then using arrays is more efficient than just using binary heap. Cool. Okay, theoretical results. What people know about time complexity of minimal spanning trees? Just to keep you, I don't know. I will not explain how it works. Just explain what some algorithm. There are some algorithms which have this time complexity. Okay, it's possible to make algorithm which works in this time complexity. It uses not the disjoint unit but another. It uses some very strange heaps. It's complicated. So you may read about this, but it is complicated. So it's possible to make algorithm which works in almost linear time. So it's m multiplied by inverse Ackermann function. It is the same function like we used in the like in union find, but it comes from different data structure. What else? It is possible to make a randomized algorithm which works in linear time. Maybe we'll talk about this algorithm. It's actually not this algorithm is not that complicated. We may discuss this algorithm. It's actually quite simple. Now, what is interesting? We don't know if it's possible to solve it in linear time without randomization. So there is not an algorithm which is non-linear time complexity, which is completely determined. But if it is possible, then there is an algorithm which do it. There is another algorithm which is proved to be optimal. So we can prove that it's impossible to make this. So if there is some optimal time complexity for non-randomized algorithm which solves MST problem, then this algorithm have the same time complexity. It kind of uses these trees of, how it's called? Decision trees, yeah. So it's kind of used, if you look on the decision tree about building the minimal spanning tree, like we discussed when we talk about sorting algorithms, yeah, maybe you remember. So basically what you do when you construct minimal spanning tree, you compare some edges. You need to compare these edges, compare these edges, compare this edge, and then you have this minimal spanning tree. So if you look on the minimal possible number of these comparisons you need to make to build this minimal spanning tree, then there is an algorithm which have the same time complexity as the minimal height of possible decision tree for the minimal spanning tree. But unfortunately, we don't know what is the minimal possible height of the decision tree. So there is an optimal algorithm, but no one knows its time complexity. That's the current situation. By randomizing, I mean that time complexity is not m, but the expected time complexity is m. So the time is not fixed. The time of this algorithm itself is a random value. So that, like in quicksort algorithm, yeah. So in the time complexity of quicksort algorithm is n log n, but it's not the worst case running time. It's like average running time, yeah. It's like expected value of the time. It's the same here. So the expected time complexity is linear. Yeah. Good. Oh, we spent a whole hour for this. I have one more algorithm. One more algorithm is Boruvka algorithm. I just cannot skip the Boruvka algorithm. Let me explain one more algorithm for building minimal spanning tree because it's cool. Okay, the final algorithm for the minimal spanning tree is Boruvka algorithm. Again, let me check the spelling. Boruvka, yeah. It's a very cool algorithm because it was invented before the computers were invented. So, Boruvka invented this in the early, in the beginning of the 20th century. He just needed to build actually the minimal spanning tree, to build something like electrical network in his town, something like this. So he invented this algorithm. Very simple algorithm. Let's draw a graph. Let's draw a graph. I love to draw graphs. Something here, and let's put some weights. Let's say 1, 5, 10, 7, 3, 2, 7 here, 6, and let's say 3, 6, 7, 8, 10. And something here, let's say 4 and 5. Mean for trees for positive, for instance, it works. So. Yeah? No, the same algorithm, we actually never used that the costs are non-negative. You can do the same algorithm with negative costs. It doesn't matter. If you just want to build the minimum spanning tree and you want to, for example, if you want to find the maximal spanning tree, you can just make a negative of all the values and build the minimal spanning tree. It also works. No. We never used non-negativity, so it's actually useful for. The only thing we used is the linear order of all elements. Yeah. Let's see. So we have this graph. Very simple idea. Let's take any node and find the minimal edge connected to this node. Then, just by using the same lemma, we need to take this edge into minimal spanning theory. So let's take any node, iterate for all edges connected to this node, find the minimal edge, and add this minimal edge to the spanning tree. So we add this edge we add this edge. Now for this vertex we find the same edge. For this vertex we find this edge. For this vertex we find this edge. For this vertex we find this edge. Here we find this 5. Here we find this 3. Here we find 7. Here we find this 4. Here we find 4, and so on. Well, of course I have Russian accent, I'm Russian. Now, let's take all these nodes and put them into the minimal spanning tree. Okay, what we did, we just used the same lemma, but used it not for single cut, but for all cuts. So we take any node, look on the cut between this node and everything else, and find the minimal edge in this cut. That's all. Now let's see. We can do it in linear time. So in linear time, we can iterate over all edges for every node and find the minimal edge for every node. So we can add all these edges into the minimal spanning tree in linear time. Next. Now it's not a tree. Yeah. So we add all these edges into minimal spanning tree, but right now it's not a tree. By the way, what is the cost of this edge? Let's say 8. So what we do next? We just we need to compress every connect component into a single node, like we did before. So let's look on the connect components in this minimal spanning tree. We can compress it into a single node. So starting from here, we take all these nodes, put them in a single component. So we need to take this, put in a single component, put this in a single component, put this and this. So we have 4 connect components, and put these edges between them. So we have this 10, and this 7, and this 3, and this 7, right? And here we have 6, 8, and 10. And here we have 5 and 8. So just compress every connect component into a single node. Could be the components not a tree. If all the weights are different, then it's impossible to build a cycle. You can easily prove this. If you have equal weights, then sometimes, for example, here, you can take for this node take this edge, for this node take this edge, for this node take this edge, and you will have a cycle. You can fix it easily just by having like the second something like priorities. So if you have several edges with the minimal cost, you need to take some priorities for them. Just sort them by the index of the node or something like this. So if all weights are pairwise distinct, it is impossible to build a cycle. You can easily prove this. Now, you compress all the connect components into nodes and then repeat the same process. So for this graph, again, you take each node and find the minimal edge. For this node, you have this edge. For this node, you have this edge. For this node, you have 6. For this node, you have 5. And that's all. And now you just uncompress. Yep. all these connect components back here and add these edges into your original graph. Let me use another marker. So you have this, you add this 6, you add this 5, and this 3. And now you have a minimal spanning tree. That's all. That's the whole plan. Now, what is time complexity? So each iteration takes linear time. No, because you need to iterate over all edges for every node. You can find minimum in linear time. Yeah. So for each node, you iterate over all edges, find the minimal edge, add it to your spanning tree. So you can do all this in linear time. And now, when you compress all the connected components, the size of the graph will be decreased. It will be decreased at least twice. So if you have n nodes here, then here you have no more than n over 2 nodes. Because each connected component can contain at least 2 nodes. Okay? So the number of nodes will be decreased at least twice. That's all. So the number of iterations will be at most log n. So total time complexity will be n log n. Cool. That's all. That's Baroque algorithm. Again, it's very simple. It's very efficient. In practice, that's the worst case time complexity. So in worst case, each connect component will contain only 2 edges. In practice, you will have big connect components. Like here, you have connect components of 4 nodes and so on. So in practice, you will have some big connect components. So the number of nodes will be decreased even more than twice. So it's very efficient in practice, and you can add some more heuristics to this process. So it's a very cool algorithm. It's widely used in practice. Cool. Do we have enough time? I believe we do. We have one more problem to discuss. Any more questions by now? I will raise that hand. Okay, we'll have 20 minutes. Will it be enough? No, okay. We'll try. So I want to discuss one more problem. It's a little bit more complicated. It looks kind of the same, but it's a little bit more complicated. It's look the maximal, how it's called? Arborescence? I forgot the word again. Arborescence. Yeah. Yes, arborescence. Yeah. Yeah, right. I always forgot this word. It's kind of strange word. We'll talk about minimum we'll talk about minimum arborescence problem. Very strange word. What's the problem about? Let's have a graph, but not undirected graph, but directed graph, and fix one node of the graph. Let's say this node is the source of this graph, like we did in the Dominators problem. Yeah? So we have a directed graph and one single node, which is the source. It's not S. Something here. Yeah, good enough. And again, let's have every edge has a weight. So let's put some weights here. Let's say let's have 2 edges here, just to make it more interesting. Let's say 5, 6. What I want to do, I want to have, let's see, 3 and 1. Yeah. Sorry, let's say 6 here, 5 here. Yeah, good enough. So let's say 4, 6, doesn't matter. Yeah, okay. Let's see, 3, 7, 8, why not? And let's say 2 and 4. Good enough. And 5. Okay, now what is the problem? I want to find something like a spanning tree. I want to find a tree which is rooted in node S and contains all the nodes of the graph. So I kind of want to find a, like in DFS tree. So I want to find a directed tree with root in node S, which contains all the nodes of the graph. I don't want to try this picture. So I want to find something like this. I want to find a tree which is directed in S and contains a paths from node S to every other node. I want to build something like this. And I want the total cost of all edges in this tree be as minimum as possible. Again, the intuition is very simple. So imagine you want to have a path from node S to everything else. So I want to have a path from S to all other nodes. So the minimal structure which makes all the nodes accessible from node S is a tree rooted in the node S. Yeah. So if you have some node not in this tree, you can remove this node and the connectivity will stay the same. Yeah. So I want to be able to move from node S to every other node. And I want the total cost of all these edges be as small as possible. That's the problem. Okay, is the problem statement clear? Huh? So I want to build a tree like this with minimal total cost of all edges in this tree. Yes? So the problem looks kind of the same like minimal spanning tree, but unfortunately it's much more complicated. Why it is more complicated? No, because you kind of don't have this lemma like before. So if you try to apply the same lemma like before, so you have this again. You have this set A, you have this set B, and you try to find this edge UV, direct edge again. Here you have direct graphs, you have direct edge, and you kind of want to say if I have this tree. Then in this tree I have path from U to V, but you actually don't have this path. You have path from S to every other node, but if you take node U here and node V here, you don't have path from U to V. So you can't apply the same lemma here, because the path is directed. So it's a little bit more complicated. It's actually much more complicated. And the cool thing that it's actually solvable in polynomial time, and we will discuss the algorithm right now. So it's actually not that hard algorithm. So well, let's do it. Let's just do it. Whew. Let's go. So the algorithm, it's Edmonds algorithm. We will talk about Edmonds invented some algorithms for these problems and also for matchings. So in the next semester we'll talk about how it's called, like a match. We'll talk about matchings in the graph, and we'll discuss another Edmonds algorithm. It actually looks kind of the same, but for a completely different problem. Let's go. So let's go. First, let's try to do something with all these weights. We can do the following operation. We can take some node, which is not the root. Let's take some node V. Let's look on all ingoing edges. This node, so all these edges. Yes, we'll talk about general graph matchings in the semester. Yeah, we'll totally do it. It's not that hard as it looks like. We'll do it next semester. So let's take any node of the graph and look on all ingoing edges. Exactly one of this edge will be in this tree. So for every edge except the root, there is exactly one edge going in this node. So if you look on all ingoing edges, exactly one of these edges will be in this final tree. So what you can do, you can add the same constant to all these. So you can take all these edges and add the same delta to all the weights of these edges. If you add delta to each of these edges, then the total cost of this tree will also be increased by delta. Yeah. But because you have this v somewhere here, so exactly one of these edges will be increased by delta. So again, this operation do not change the result. It do not change the final tree. Because exactly one of these edges will be taken. If you increase them all by the same delta, the final tree will be increased by the same delta. So the minimal tree will stay the minimal tree. So it's the safe operation. You can do it at any point. You can take any node and add delta to all ingoing edges. It will not change the final result. That's the whole idea. And now we'll try to apply this idea here. So let's take any node. Let's take this node. This node has two ingoing edges, so it's have 3 and 6. Let's just add -3 to all these edges. So we'll just decrease all the edges by the minimal weight of all edges. So let's take these two edges and decrease the weight by 3. So we take -3 here, it will be 0. Take -3 here, primly here. Now just apply the same procedure to all nodes. So we'll try to make as many zeros as possible. So we take this node, we have 2 and all, so we'll just decrease this to 0. Here we have 5 and 3, we decrease it by 3, so we have 0 and 2. Here we have 1 and 6, decreased by 1, so we have 0 and 5. Here we have 6 and 3, so we have 0 and 3. Here we have 4, 4, 5, 7. Okay, it will be 0, 0, 1, and 3. And here we have 5 and 8. It will be 0 and 3. Yeah? Looks fine. I don't like these two zeros. Maybe it's fine. Let's make this one. I don't like I have two zeros. I don't know how to. That happens when you have the same cost for all edges. Let's have all different costs just for simplicity. Now, okay, let me write the algorithm here. So we iterate for all edges for all nodes. Let's make it for all b. Let's take the delta is the minimal cost going in node v. So for all uv. So for each node we find the minimal ingoing edge, and now we take all uv, we just take uv minus equal delta. Okay, that's the first step. Now we have a lot of zeros. Let's mark all the zeros. We have 0 here, zeros here, we have zeros here, and here. So our graph contains a lot of zeros. Case 1. If let's look only at the zeros. So let's remove everything but zeros. If every node is accessible from S using only these zeros. Reachable from S by zeros. if you can reach every node from the node S using only zeros, then I claim that the answer is actually 0. Why? Because you can build a tree from node S which uses only 0 edges, so the total cost of this tree is 0. And you cannot have a tree with cost less than 0 because all the weights are non-negative. So if in this graph you can access every node from node S using only zeros, then you can build a tree with total weight equal to 0, and you can't make it less than 0. So the 0 is the optimal answer. Build tree of zeros. Return. Nice. But sometimes it's not the case. Sometimes you have something like this. So you have some strange graph, and not every node is accessible from reachable from node S. For example, here, if you start from node S, you can only reach this node and this node, and all these nodes are not reachable from node S. Then I claim that if some node is not reachable from S, then you have a cycle. For example, here we have two cycles. We have this cycle and we have this cycle. So if some node is not reachable from S, then there is a cycle of zeros. Why it is true? Well, because let's find some node which is not reachable from S. Let's take some node V. It is not reachable from S. So every node has some ingoing edge which is 0. So let's take 0 node going inside. Now for this node, let's take another node which is ingoing to this edge which has 0, and so on. So each time we take some ingoing edge with 0 cost. Every node except S has at least one ingoing edge which has 0 cost. So we always can take some 0 edge ingoing to all of them. And so at some point we will go into loops because we have fixed number of nodes. So at some point we'll find node which we visited before. Here. So at some point we'll find something like this. And now we have this cycle. So if not all nodes are reachable from S, then there is a cycle. Let's find this cycle. It's easy. Cycle. Zeros. Zeros like this. Nice. So let's find this cycle of zeros. If we have several different cycles, let's find any of them. So let's find any cycle of zeros. Now, let's see. Inside this group of nodes, every node is accessible from every other node, because you have this cycle. So inside this group, every node is reachable. So what we can do is we can compress this cycle into a single node. Yes, if you have multiple cycles, you can compress all of them. Let's do it here. Yeah. Let's compress all cycles, just for simplicity. Here, we have these two nodes. We compress them into this fat node. We have these three nodes. Let's find this. We have these three nodes, compress them here. We have this node, and we have S. So this node is compressed, these three nodes compressed, and this node is these two nodes compressed. So we have here, we have 1, here we have 3. And yes, here we have 0, 3, 3, 0 and 2, and here we have 2 ones actually, and 5. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, 10. So we compress these 3 nodes into 1 node here, and these 2 nodes into 1 node here. And now just repeat the same process. We take this graph. For each node, we decrease all the costs by the minimum of them. So for this node, minimum will be, so we have 1, 3, 3. So minimum is 1. So we decrease everything by 1. So we have 0 and 0. Here we have 2. Here we have 2. Here, and for this node we have 3 and 5, we decrease, let's say 0 and 2. And again, we look on all zeros. We look at all the 0 edges. So we have this 0 edge, this 0 edge, this 0 edge, any of them actually, and this 0 edge. And now in this graph, everything is connected, every node is reachable from node S. So this is a valid tree, yeah? So here we have a tree of zeros, and we can have less than 0. So this is the optimal tree for this graph. Now what we need to do is to move from this answer to this graph. How can we move this answer here? We need to uncompress each of these fat nodes. So we take each of these fat nodes and uncompress them into these cycles. Let's back to use another color for this. So I need to add this edge here. And I need to add this edge here. It's one of these edges. This, for example. So I just take all edges from this graph and put them back to this graph. And now I don't have a tree. I have something with cycles. So I need to get rid of these cycles. How to get rid of the cycles? It's quite easy. So for each cycle, you have one ingoing vertex, this. So it's this. So for this fat node, you have this ingoing edge. So when you uncompress this fat node here, this edge will be going into one of the nodes of this cycle. So for this node of the cycle, you now have two ingoing edges. You have this edge and this edge from the cycle. So to make it tree again, you just remove this edge from the cycle. So you just remove this edge from the cycle. And now you fix this. And also you do the same here for this node. So this node is going from here. So you have this ingoing edge. You move it to this graph. So it's this node. So for this node now you have two ingoing edges. You just remove the second. Just remove this one. And now you have a valid tree. So this is a valid tree for this graph. That's all. That's how you build the minimal arborescence. Yeah? Did I say it right? I think I did. That's all. That's the whole algorithm. Again, how the algorithm works? You take all the nodes of your graph, find the minimal edge, reduce all the cost by this minimal edge. Now, if all the nodes are reachable, then you just build tree of zeros and you're done. If not, then there are some cycles. You just compress all the cycles and repeat again. Repeat the same process. Repeat the same process. If you do it like this, like using this simple procedure, Well, if you just do it in a simple way, just each time you do all this, then the total complexity will be like this. So all these can be done in linear time. So I claim I can do this in linear time. Just say M. You can do this in linear time. You can check this in linear time, and you can compress cycles in linear time because everything else in linear time. So you can do all these operations in linear time. And when you compress cycles, you reduce number of nodes in your graph. So you can't reduce the number of nodes more than n times. So if you just apply it like this, time complexity will be n. So just a very simple implementation of this will give you an time complexity. Can you do it faster? You actually can. To do it faster, one of the ways to think about it is just to modify this algorithm. What you need to do is basically remember the current state of your tree. It's not a tree, it's something strange. Yeah. So you need some way to detect the cycles, and you need some way to compress the cycles into single nodes. No, because here in these operations, you only need to update this for these new fat nodes. For all these single nodes, you don't need to update this minimum, because for each of these nodes, on the previous step we had this operation already done. So we need to make this operation only for these new fat nodes. So this is actually not a problem. After you compress the cycles, you need to apply this operation only to these new fat nodes. Yeah. So this is actually not a problem. This is actually kind of problem. So for here, you need to check if your current situation is actually a tree rooted in S. You can actually do it using some tree structures. And here you need to find some fast way to detect the cycles and compress them. Also doable, but it's kind of tricky. There is another way to think about this algorithm, which is kind of easier way to build fast algorithm. Do we really want to explain? Okay, let me explain this. If you want to build fast algorithm, you need to do it in slightly different way. So what's the problem here? Problem here is that I'm trying to build a lot of things. So I'm trying to build all these structures, and then just compress the small cycle. So I spend a lot of time just by remaking the whole graph, and then just compress, in the worst case, I just compress two nodes into one. So in the worst case, I have a single cycle containing only two nodes. So I just compress two nodes into one. That's not efficient. What you want to do is to not to make all this picture, but only create a small part of this picture. And if in this small part you have a cycle, you compress it immediately. So you can do it like this. You start from some node, take some node. Now each time you take all ingoing edges. Let's apply this operation only to this single node. So you take all ingoing edges, take the minimum, decrease all the values by minimum. Then you have a zero edge. Then again, for this node, do the same trick. Take all ingoing edges, take the minimal one, and decrease everything by this. So every time you take the zero edge, so you have this path of zeros, not the whole graph of zeros, but only path of zeros. That at some point you may have one of two situations. You may reach the point S. If you reach the point S, then this is the correct part of your final. Yeah, this is correct part of your final tree. So you just left this as it is, take another node V and start from this point. Or you may have you may have loops. So maybe at some point you will have something like this. No. So maybe at some point you find zero edge, and then you have a loop. If you have a loop here, then you need to find all the nodes on the cycle and compress them into single node. But after you compress them to the single node, you don't start from scratch. You should not start from this node V, but you start from here. because you already have this state, a good state. So you have the node V and then some path of 0 edges to this node. So you compress this cycle here. It's kind of stack. You have this stack of nodes, and if you have cycle here, you compress these top nodes into single node and put this new fat node in the top of the stack, and let's continue from this point. That's kind of how you get a faster algorithm. No, it's actually a little bit more tricky, because you need some good data structures which will allow you to find the minimal edge among all ingoing edge. And you want some data structure to remember all your ingoing edges. And this data structure should allow you to find the minimum and decrease everything by this minimum. So you need something like heap or binary search tree just to remember these ingoing edges. And when you compress this cycle into a single node, you kind of need to take all these lists. So for each of these nodes, you have some ingoing edges. Yeah. So when you compress these nodes into a cycle, you want to kind of concatenate all these lists into a single list of ingoing edges. So you need something like mergeable heap. That's also possible. There are mergeable heaps. So you can use mergeable heaps to store the ingoing edges for all of these nodes. So when you combine these nodes into a single node, you just merge all these mergeable heaps into one single heap, and then you're done. And now in this heap, you can do two operations. You can find the minimum, and you can reduce all the values by the same minimum. That's also possible. And if you do it like this, you will have the time complexity like m log n. So that's doable. That's actually quite, it's not that hard to implement. So if you already have implemented some mergeable heaps, it's actually, no, it's not that hard. You just do this. You have this stack of nodes. Each time you add, you try to add this extra edge. If this node is already in your stack, then you have this cycle. You just remove all the nodes from the top of the cycle, compress them, merge all these heaps, and put this new fat node in the top of this. It's actually doable. It's doable. Interesting thing, you can actually improve this to work in n log n plus m time. And the way you do this is actually by using Fibonacci heaps. But it's not as easy as it looks. So you can just apply Fibonacci heap and see, because here you actually, each time you need to remove a minimal edge, and when you compress the cycle into a single node, you have a lot of loop edges. So when you have edges inside this component, like here you have some edges, yeah. When you compress all these nodes into single node, you will have a node and some loops. And these loops may be the minimums. So when you remove these loops from this heap, each time you spend log n time to remove these loops from this Fibonacci heap. And removal from Fibonacci heap costs you log n time. So if you just try to apply Fibonacci heap to this algorithm, you will have m log n time again, because for each edge you need to spend log n time to remove from Fibonacci heap. So it's a little bit more complicated. You don't want to store all the edges in this Fibonacci heap. You kind of want to select some edges. So the idea is like we used in Prim algorithm. So for each node we remember some good edge, and we put only these good edges in Fibonacci heap, and then we will do something in it. And then we need to modify Fibonacci heap, because we kind of move elements from one heap to another, and we can do it in gradual Fibonacci heap. So we need to modify the Fibonacci heap, and that's not what you want to do usually. Fibonacci heap is complicated by itself, but for this algorithm you need to some modified Fibonacci heap. So that's cool algorithm. I highly recommend to read the paper about this algorithm if you're interested in this topic, but This is complicated. So you can do this, but it's complicated. I'm not sure if it is possible to make it faster than this time. I believe there is no known algorithm faster than this, but I'm not sure if there is a proof that it's impossible. I think it's not. So maybe it's possible to do it faster, but we don't know. I didn't check. Maybe there is a proof that this is an optimal algorithm. I'm not sure about this. But that's the best algorithm I know. So maybe it's actually the optimal. Okay, I think that's all for today. Oh.